Hello everybody, my name is Michael Körber from the Database Research Group at the University of Marburg, and today I present our approach on index-accelerated pattern matching for event stores. This work was supported by the Priority Program on Scalable Data Management for Future Hardware of the German Research Foundation. I will start with a few introductory slides to motivate our work and briefly introduce some key concepts. Then I will present our query processing approach and show how indexes can be used to answer event pattern matching queries. A major part of our work is a cost model and an index selection strategy that allows us to determine efficient query execution plans. To stay in time, I will only briefly sketch those aspects. Before I conclude this talk with a brief summary and directions for future work, I will present the most important results from our extensive experimental evaluation. Let's start with events and event streams. Basically, an event represents an observation from the real world that occurred at a specific point in time. An event stream is then a temporally ordered sequence of homogeneous events. There are many examples for event streams. For instance, a stock ticker that reports all price changes for every security as shown here naturally generates an event stream. One of the most important and powerful stream processing operations is event pattern matching that allows to detect interesting subsequences of events in a stream. Event pattern matching support is found in most complex event processing systems and recently became part of the SQL standard. Technically, this operation performs regular expression-based pattern matching on the stream. In contrast to classical string matching, the symbols used in the pattern are not static, but dynamically defined with the query. Every symbol of the alphabet is associated with a condition, and if this condition holds for a given event, the corresponding symbol is emitted. Moreover, event pattern queries define a time window in which the match must occur completely. To make this idea more clear, I prepared a small example. In this example, we want to detect a steadily increasing stock price, starting at less than $100 and climbing above $200 within one day. I used SQL's match recognize clause to define this query. The pattern is specified as a regular expression over three symbols. We expect exactly one occurrence of the A symbol, followed by 0 or more B's, and finished by exactly one C. The within clause specifies the time period in which the pattern has to occur completely. The alphabet is specified using the define clause. Note that the predicates A and C are simple thresholds, while B uses a predicate that refers to a previous event in the stream. This allows us to detect trends in certain attribute values of the events. Finally, the measures clause specifies the shape of the query results. In our case, we report the starting and ending price of the stock. In the recent past, lots of attention was paid to the efficient online evaluation of continuous streaming queries. However, in many cases it is important to also store incoming streams and efficiently support ad hoc queries on historical stream data. Analytical queries are such a case. For instance, if you want to find out how often a specific stock pattern occurred over the past year. Another example is the tuning of online queries. If you rewrite your query for performance reasons, you must ensure that the results of your rewritten query are in line with those of the old version. What those examples have in common is that you want your results as quick as possible. Thus, simply replaying the entire stream into an online stream processing engine is not an option here. To address those scenarios, event stores appeared recently. Those are special-purpose database systems optimized for storing, indexing, and querying high-volume, fast-arriving event streams. They provide support for ad hoc streaming queries such as time travel queries, temporal aggregation, sliding window aggregation, and even pattern matching queries. However, while many other query types get optimized, event pattern queries are currently answered by replaying the entire stream into an online engine. This is where our approach applies. Our goal is to reduce the amount of data to replay by pre-filtering the stream using indexes. Thus, we only need to replay the remaining regions into an online algorithm instead of the entire stream. To do this, we need to tackle two main challenges. First, since the alphabet is dynamically defined with the query, it is impossible to build indexes over symbols upfront. Thus, the question is how to exploit indexes on stream attributes for pattern queries. Second, heavy index utilization quickly leads to query runtimes worse than a full replay. So the second challenge is to provide suitable cost estimation and index selection methods. Let's now have a look at our query evaluation approach. Our approach is based on a generic index architecture as found in most relational database systems. Events are stored in a primary index ordered by the timestamp. This allows us to quickly find and replay relevant stream regions. In addition to the primary index, there may exist multiple indexes on secondary stream attributes. We use those to find events that match the pattern's symbol conditions. To relate multiple results from such index queries with each other, every entry of the index not only consists of the indexed attribute value, but also contains timestamp and sequence information. I explain our method using this tiny example stream. Assume we want to find the pattern A, B star, C. As you can see, there are only two matches. In addition, there are two more occurrences of the A symbol. Obviously, when doing a full replay, lots of irrelevant data is read and streamed into the online algorithm. Instead of replaying the entire stream, our approach works as follows. We select a symbol, A in this case, and query the corresponding secondary index. This query returns us the timestamps of all occurrences of symbol A. In the next step, we use the window constraint and construct a replay region around the found symbols as shown in the bottom image. This reduces the data to read to 4 regions. However, there are still 2 regions that do not contain a match of the pattern. We can fix this by issuing another index query for symbol C. Since we find no C symbol for replay regions 2 and 3, we can exclude them from the replay completely. When using multiple secondary index queries, the question is, can we combine those results efficiently? And the answer is yes, by using a sort multi-way merge approach. We first sort the results of the index queries individually and then create the replay regions via a multi-way merge as shown here. The first element is symbol A1 with timestamp 1. By picking the next element, C1, and comparing it to A1, we find out that this combination exceeds the time window of 3. We proceed with A2 and find a matching C with C2. Hence, we obtain the replay region covering the time between 15 and 17. We proceed until all results from the secondary index queries are consumed. Let us now get to the cost model. As can be seen in the graph on the right, using all available indexes quickly leads to total query execution cost that exceed the cost for a simple replay. The basic observation here is that the more symbols we find using secondary indexes, the higher the index access cost get. At the same time, the replay regions shrink or get less. So the question is, what is the optimal selection of indexes to get the least total query execution cost? As a first step, we need to estimate the total execution cost for a given set of index queries. Those costs consist of 4 parts. The cost for querying the secondary indexes using the symbol conditions, the cost for generating the replay intervals using the sort merge approach, the cost for reading the replay regions from the primary index, and finally, the cost for evaluating the pattern query. In this talk, I focus on the estimation of the primary index access cost. However, the remaining components are thoroughly discussed in our paper. To estimate primary index access costs, our idea is to estimate the fraction of the stream that will be covered by the replay intervals and derive the access cost from this value. To estimate this coverage, we first need to estimate the number and the average length of the generated replay intervals. Therefore, we make the following assumptions. First, we know how selective the conditions of the pattern symbols are. Second, the symbols are uniformly distributed across the entire stream. And third, the arrival rate between two consecutive events of the stream is constant on average. Now let's first see how to estimate the number of replay intervals. When using only a single index query, we simply need to multiply the condition's selectivity with the total number of events in the stream. For two index queries, say for symbols A and B, this gets a bit more complicated. We need to find out how many of the A occurrences are followed by a B within the time window. Due to our assumptions, the inter-arrival time of Bs is constant on average, and we can model the arrival of Bs as a Poisson process. Hence, the probability that a B follows an A within the window is exponentially distributed. For our estimation of the number of replay intervals, this leads to the equation shown in the blue box at the bottom. I will stop the discussion on the number of replay intervals at this point and refer to our paper for a description on how to extend this idea to more than two index queries. Let's get to the estimation of the interval length. Assume we have n symbols, A1 to AN. Depending on the actual index selection, there are three cases for the interval length. If the selection contains A1, it is sufficient to enlarge the replay regions from A1 to the future by the length of the window, since no events earlier than an occurrence of A1 contribute to a match. Hence, the length of the replay intervals in this case is the length of the window. Similarly, if the selection contains AN, the replay regions are extended by the length of the window into the past, since no relevant events exist after an occurrence of AN. However, if none of those symbols is selected, we need to look backward and forward, and hence the length of the interval is approximately twice the size of the window. Having estimated the average length and the number of replay intervals, we are now able to estimate the overall stream coverage. We do this by partitioning the stream into disjoint buckets. Each bucket spans the length of one of the replay intervals. If we then uniformly distribute the intervals over those buckets, the coverage is simply the ratio of filled to total buckets. Before we get back to the index selection, let's see how to weaken the assumptions we made in order to make our approach applicable to many different stream characteristics. Our idea is to support our method with a temporal histogram. We temporally partition the stream into disjoint substreams and maintain relevant statistics such as the average event arrival rate or the attribute value distribution for each of those substreams. Then we estimate the overall stream coverage by combining the coverage estimation for each of those substreams. This way, we require our assumption to hold only within a substream and not on the entire event stream. Now that we are able to estimate the total execution cost for a given set of indexes, the next task is to find a set of indexes that minimizes this cost. There exist several standard methods for solving this task. For instance, we could simply enumerate all possible combinations. However, the runtime of this approach is exponential in the number of possible index queries, which leads to very high costs, even for moderate number of symbols. Other approaches that only consider the total execution costs, like Greedy, that selects index queries in descending selectivity order, or dynamic programming that combines optimal solutions of subproblems, fail to find the global optimal solution. The reason for this is that the pruning power of a symbol does not only depend on the selectivity of the corresponding condition, but also on the symbol's position within the pattern. A detailed explanation of this would be a bit lengthy, so we refer to our paper for details on this aspect. To tackle this problem, we designed an algorithm that is able to determine the optimal solution with an expected runtime of m cubed log m for m possible index queries. Our algorithm exploits two observations. First, the optimal selection is within the 2D skyline of cost factors 1 and 3. Those were the axis costs for the primary and secondary index axes. Second, the 2D skyline for all possible index queries can be efficiently computed from the skylines of two disjoint subsets of index queries. As a consequence, we were able to use a dynamic programming approach to compute the overall skyline and extract the optimal set of index queries from this result. Let us now have a look at two important results from our experimental evaluation. In the first experiment I want to show, we compare the overall query runtime of our approach with a pure replay-based query evaluation. We integrated our index-based evaluation method into three systems: ChronicleDB, that is our own event store implementation, Apache Flink, and a commercial database system with support for Match Recognize. We executed pattern queries with 6 to 9 possible index queries on two real-world datasets. The first dataset contains around 7 million crime reports from the city of Chicago. In this case, we used a pattern to detect a series of possibly related crimes. We specified certain crime types and required them to occur in close spatial proximity within half an hour. The second dataset contains trajectory data from an airplane and consists of roughly 50 million events. For this dataset, we formulated a pattern to detect landing maneuvers. In the figure on the right, we compare the runtime of our index approach with a pure stream replay. The key observation is that our approach is able to speed up the queries independent of the used system. Especially for the first crime query with 6 possible index queries, the speedup reaches 2 orders of magnitude. The second experiment I brought compares our estimated total execution cost with the actual query runtime for all 512 possible execution plans of a crime query. The figure here shows the runtime for every execution plan. The plans are ordered by the total execution cost as estimated by our cost model. This clearly shows that our cost model is able to create a very good ranking of plans. Especially the best plans were estimated very accurately. In the right corner of the figure, we see the effect of using too many index queries. In those cases, the total execution time exceeds the runtime of a full stream replay. So let me summarize. We developed an approach to accelerate event pattern queries in event stores. We show how to use well-known index structures to reduce the data to load from secondary storage. Moreover, we developed a cast model and an index selection strategy to find the optimal set of index queries for a given pattern query. In the future, we plan to extend our approach in 3 aspects. First, we want to add support for a group by clause to be able to query multiple logical streams contained in a single physical one. For instance, to analyze each stock individually in a ticker containing multiple stocks. Second, our current cost estimation for online pattern evaluation only supports one of 3 so-called event selection strategies. In the future, we want to add estimation methods for the remaining 2. Finally, we want to add support for a wider range of symbol conditions. Thereby, we will focus on relative predicates that refer to attribute values of previous events because they are used in many real-world pattern queries. So, that's the end of my talk. I thank you for your attention and I'm looking forward to your questions.